everybody. So I work at VTT and especially in large-scale European research projects together with the automotive industry where we develop driver support systems and more recently automated driving. So my presentation today is about the use of deep neural networks in that work and also safety validation. So I'd like to highlight first that AI has been able to give us some wonderful steps in the last 3 years. And me and my colleagues, we were a little bit maybe more pessimistic about what could have been achieved by today. Certainly there is still work to be done. Certainly neural networks have a wide application range, and even though that is the case, they are mainly used today in the vehicles for environmental sensing. So research vehicles commonly, they run a couple of algorithms, draw boundary boxes around objects, detect lanes. Sometimes we have free space detection, movement prediction. But certainly many more algorithms will be needed to extract the details of our environment. So for example, when we overtake a stopped vehicle, what would we like to know? We would want to know that are the doors a little bit maybe open, are the lights on, what is the person inside doing, where do the tires point? So certainly we are working on various more algorithms and doing data fusion based on those results. Having that type of information of the car we are overtaking would allow us to overtake a little bit closer, generally go closer and then make more advanced driving maneuvers. So we still see data fusion being the topic where we use the info from several algorithms. In some cases, we use the traditional algorithms still even in the neural network architectures like optical flow. They can give input to the architectures. As I said, the research vehicles are running mostly a couple of algorithms. So I would say that still the GPU-like of parallel processing is rather new. So the history of automated navigation is actually about the deterministic algorithms, and those we compete with. So neural networks can be certainly used for path planning, finding optimal plans quickly, control, but they have to compete with these traditional well-working algorithms. But having said so, even the end-to-end training is for AI, where the AI handles everything in driving, has moved from research to products. And these days, like my colleagues just ordered, and we were testing this system that you can buy with €2,000, gives you a highway assistance system for your car, this mobile phone type of a thing you attach to your windscreen. It really nicely handles, say, 95% of the time. Certainly, as we have discussed here today, reliability can be another story, but the performance here is what we are after. Something about the integration in our research vehicles. On the left side here, you see, well, what today's research vehicles commonly see. We have YOLO 4, that is a very popular general purpose object detection neural network, giving the boundary boxes around these road users, and then we plot LiDAR laser scanner distance measurements overlays on the image. So we see for each pixel, well, many pixels, how far they are. So we have this information that it is a car and it is some meters in front of us. And next we certainly place these objects on a map and track them, and we actually do not use these figures all the time, but we use the map-based tracking. On the right-hand side, you see this semantic segmentation, redrawing the image again based on the classes. And for us, this has been the research side, and the integration aspect here is that there are certainly more powerful segmentation algorithms out there, but they may be too heavy to compute. So this is one of the lighter algorithms, and the output is already promising, but it's still a little bit hazy and a little bit not usable necessarily straight away. It gives an extra input. So that's what we currently use in our vehicles. Of course, additionally, we have a few algorithms for lane detection and traffic light detection and so forth, but a couple of examples. And it was really much about the processing power, what we can do today with our vehicles. And I'd like to highlight that sensors and data fusion still play a big role. So upright image, you can see where a human would, from that camera, see that there's a motorcycle approaching. One figure down, you have the first recognition from this neural network that it is a person. It's not only a person, it's a motorbike. But the first box, and then at that distance, it's a little bit maybe difficult to match that the LiDAR distance to that box is something. Third picture, you certainly have all the information. You know it's a motorbike and it's a person on a motorbike. You have the distance measurements. But yeah, for sure, we are rather close already to the object. We can improve this, and unlike what Tesla and some others do, they use a zoom lens, so they have different optics, giving us more range for the objects. In the fourth picture, bottom picture, you have all the information, of course, and then in the black image you see what the LiDAR sees. Actually, it's a combination of two LiDARs. It gives us a lot of pixels there, but still, even for a human, how easy it is to see that that's a motorbike. So sometimes this can be challenging even for a human. And one extra highlight, having a winter time images here, is the weather protection. So please note these sensors are warmed and clean and weather protected and so. And actually, some of our research LiDARs, they start to drop points around -10 degrees. So the weather is still a big topic. What else seems difficult for AI? So if we just use the neural networks to copy and imitate human driving, why should the result be any safer then? So robotic safety is traditionally about bigger safety margins, even bigger than what humans use, slower speed, deterministic code, redundancy. So actually I see that automated vehicles should compensate the lack of understanding by keeping larger safety margins than what humans do. So, and there's the thing, what is a safe gap? Like the traffic law requires you to keep a safe gap. So when overtaking a cyclist, for example, is that 1 meter or 2 meters? It doesn't say in the law. We have to interpret. In addition, the law says that you should drive extra carefully if the person is a child or a drunken or disabled. And current AI, we do not have that information. So, so we have to consider how to handle that uncertainty, and the result these days is that we have to keep even larger safety margins to compensate that we do not know this. A couple of other quick examples on situational awareness, which is the main thing. Road users may suddenly appear behind visual obstructions. We have to prepare for that, and deterministic code can do that. A child running right after a football, so we do not have to brake for the football, but we might want to consider what happens after. So then something drops from the load of the previous vehicle. What was it? How heavy is it? Do we need to avoid? How extreme avoidance? And so. And the weather topics. Humans are simply better currently at understanding the weather and the friction, even though computers and sensors, we start to get this point-wise information which we can then use. My final two slides are about safety validation. This is a topic that we have entered and deal with quite a lot these days. So generally I see that safety is more easier to prove when the product uses very conservative safety margins and instead of trying to move very close to humans. So having this setup where the vehicle brakes early gives us an easier way to build the proof and documentation that the system should indeed be safe. Another point is the visibility. It really, when driving, visibility sets the limits for how fast we can drive, or can we enter an intersection that has, say, 50 kilometers per hour speed limit in the intersection, T intersection? We need to mathematically see some 50 meters left and right before we enter that intersection. How can we be certain that our sensors see the 50 meters? Sometimes we have a wall behind, like there's a building at 100 meters, and then we can conclude that if we see that, maybe we see the 50 meters. But what if there is no structure behind there to use this logic? So it can be a topic. Then other points are like how long can we lose the object tracking? I use personally in my work like 0.2 seconds, but probably we have to consider this as well in more detail. What is the maximum speed of a human? In industry we have these numbers like 2 meters per second, but it is actually about accelerations and so forth. And the reliability, I mean, we have 95% or higher rather often. It's well enough for an animal, and we break for the animal, but to only detect a child, 95% is nowhere near. So currently, realistically, in our approaches, with our sensors and AI, we detect bumps on the road. And we have to brake for the bump, we have to wait for the bump to move away, or we have to wait for the human to sort out the situation. But this is the current production phase in a way, even though we know quite a lot more. What does the big forum say? UNESE World Forum is the place to go for the vehicle regulations these days, and then for deep neural networks they only say this, that for each step of the development process you should provide safety artifacts to support the safety case. This means you build up the documentation, phase by phase, to get this big pile that somebody would, some official would give you a stamp that you are approved for driving. So it steps definition, specifications, deploy, monitor. That's the level. It's a little bit hazy still. The lesson so far, this is what I use personally, and I found that BMW uses it as well, is to, let's say, consider AI as a box that you have to put some traditional deterministic code around for safety. So, for example, collision avoidance is a traditional example of here. So the AI can drive, but when it suggests that let's drive to a wall, then the collision avoidance stops that. So otherwise, AI can drive. A couple of final notes about the safety. Even the goal in safety can sometimes be a little bit a topic still. I mean, in 2020, some 200 people died in Finnish traffic. Would it be okay if robots kill only 150, or should we have a lower number? I mean, commonly people think the target should be much, much better. That gives us rather high targets on the reliability of these systems. And then if we really look at today's fatalities, some high percentage of these are actually really difficult to prevent with any technology. I mean, you have the suicides, you have the drunken drivers, you have the young and reckless, and no technology really can cure the youth. So. On a more positive note, I mean, we sometimes consider, are we developing safety technology or just something for comfort? But really on a more positive note, I mean, the automated subways and trains so far, they have proven extremely safe, only a couple of suicides during the whole operation period. So the goals and the possibilities are there. But maybe I'd like to say something also from let's say from the infra perspective. The infra guys often hope that we can have the roads as they are, and then AI will solve it all. AI doesn't yet quite do that if we look at the products that are currently possible to put out there. So we still need better sensors, we need mathematical traffic laws, we need these regulations to consider that how far we overtake the cyclists. And then certainly we need the infra support as well. Not maybe 5 traffic lights to create a green wave for the vehicle out there, but some extra support seems necessary. So thank you for your interest. This was my talk today.